Good. So just a reminder, I think you all got the marks for homework 2. The marks for the prologue assignment should be out by now. I'll put a notice for those of you who are not sure how you can access the marks. And I don't know what's happening here. Assignment 2 has been released and will be due Sunday at the end of next week. It's a written assignment. Now today we're going to talk about logical agents. So we'll look at logic in general, models and entailment. We'll look at propositional logic. Have to compete with this, unfortunately. Equivalence, validity, and satisfiability. We'll look at some inference rules and theorem proving and resolution and converting things to conjunctive normal form, forward and backward chaining. Then we'll move on to we'll have a little bit of a break, and then we'll move on to first order logic, which introduces variables and quantifiers, and then we'll look at situation calculus. So again, I always keep coming back to this framework we discussed about different types of agents and models and planning agents, and I discussed how what kind of world model you have determines or influences what kind of planning you're going to do. And so in the current situation, what we're looking at, the world model is actually a knowledge base. So previously we looked at the world model as some sort of graph, either an explicit or implicit graph, and the planning involved state space search. So we looked at BFS, DFS, A-star search, and so on. Now, what we're concerned with now is a situation where the world model is not a graph, but it's actually a list of, it's a knowledge base. So it's a list of facts which, written in some logical language, which are true in a particular situation. And so the kind of planning that we need, so the goal in this case is we want to get into a situation where certain facts are true. And so the kind of planning we're going to do is like logical inference and forward and backward chaining and resolution and situation calculus and that kind of thing. So this is the framework that we're looking in. Now, again, we come back to this Wumpus world because it's such a sort of fruitful example. So if you look, this is a situation we looked at before. So it's obvious to us the kind of reasoning that goes on here. If I detected a breeze here and not here or here, and I detect a stench here and not here or here, then I know that the Wumpus has to be here and a pit has to be here. But the question is, how can we automate this? How can we have a framework that allows us to express these kind of statements and do this kind of logical reasoning? Excuse me, so we need to be able to represent facts such as that there's a breeze in square 1, 2, or that there's a stench in square 2, 1. And then we need rules that tell us that if there's a breeze in square 1, 2, then there is a Wumpus in square 1, 1, 2, 2, or 1, 3. So we have to take all of these rules in the Wumpus world and codify them into this formal language. And then from this we can try to deduce whether it's safe to move into square 2, 2. So the knowledge base is a set of sentences in a formal language, and the idea here is that we tell the system certain facts, and then we ask it whether certain other facts we give it certain facts and certain logical rules, and then we ask it we ask the system whether certain other facts can be deduced using those logical rules. So that's why we need this inference engine. So we have the knowledge base contains facts that are specific to a certain domain, and then ideally we have an inference engine which is general purpose and can be suitable for many domains. So going back to the rhombus world example, if there's a breeze in 1,2 and in 2,1, that means that there are no safe actions. So what we're talking about today is just about whether things are guaranteed to be true or they're guaranteed to be false or they're indeterminate. So we're not yet talking about likelihood or probability, but in week 8 we will talk about probability. So if you get into this situation where not sure what's going on here. If you do get into this situation where there aren't any safe actions, if you're cautious, you can just say, well, I'm going to give up and go home. But if you're brave, you can try to minimize you can just try to take some action, but try to minimize the risk. So later we'll talk about how to calculate those probabilities. Let me see here. I'm probably going to have to switch to the desktop because something, I don't know if this is a dodgy connection or what. I'm just going to attempt to switch to HDMI, and then if that doesn't work, we'll go to the desktop. That didn't do anything. Okay. So just imagine that you've got a pit. Hang on. Just bear with me for a moment while I try to find... okay. Let's see if we can get the okay, we've got the internal computer. See if I can find it here. This is just... unbelievable. Okay. As I was saying, now you have the sort of feeling that this middle square is probably a bit more dangerous than the others, right? Because I've detected a breeze here and here. Well, we don't know. It could be that there's it could be that there's a pit there and a pit there. It could be that there's pits on all three squares. There could be pits here and here, but not there. There could be here. There's 7 or 8 different possibilities. We kind of have a feeling that it's a bit more likely that the pit would be here rather than here or here, because we have two pieces of evidence supporting the hypothesis of a pit here, and only one piece of evidence supporting a pit here. So we sort of have an intuitive feeling that this square might be a little bit safer than that square, but as I said, in week 8 we'll talk about how to actually put a number on that, how to quantify how much safer this is than that. Okay, but at the moment we're just saying that none of these can guaranteed to be safe. Now, we looked at this situation before as well. What happens if you detect a stench? We talked about how you shoot an arrow and then it's kind of like an excluded middle, so if the wumpus was there, then the wumpus will die. And so we'll talk also about how to deal with this kind of situation, how to reason about future states, and if we take an action now, what things are going to be true in the future. All right, now, a knowledge-based agent, we have to be able to represent states and actions and so on. We have to be able to, when we perceive something, we have to be able to add new knowledge to the knowledge base. We have to be able to update our internal representation of the world when new information becomes available. We have to be able to deduce hidden properties of the world, things that are currently true but we can't see directly, we infer indirectly. We have to determine appropriate actions, and as I said, for things like this, we have to actually be able to reason about the effect of our actions. All right, now there's a lot of terminology involved in logic. So a logic is a formal language for representing information. So we talk about syntax and semantics. So syntax simply tells you whether a sentence is grammatically well formed. So x plus 2 greater than or equal to y, that's a well-formed sentence. We don't know whether it's true or false, but it's sort of it follows the rules of grammar. Whereas a sentence like this, well, this is just what Noam Chomsky called word soup. You know, these symbols are jumbled up in a random order, and this doesn't actually have any meaning, right? So that's the first thing, is whether things are syntactically correct. And then semantics is about whether things are true or false. So this x plus 2 greater than or equal to y, whether that's true or not depends on the values of x and y. So if x is 7 and y is 1, that would be true. But if x is 0 and y is 6, it would be false. Now, then we have a few other sort of interesting symbols here. So there's this entailment symbol, which looks like a table on its side, the two legs. And if we write this, what this means is that the knowledge base entails alpha. So if a certain sentence alpha. So the knowledge base is a set of sentences that are true, and then if we talk about a certain sentence alpha, what this means is that in any world, so we sometimes talk about world and model. A model is, the word model usually just refers to an assignment of truth values. So in any model in which the knowledge base is true, alpha is also true. That's what this symbol means. So alpha is true in all worlds where the knowledge base is true. So we're going to use the words world and model interchangeably. So x plus y equals 4 entails that 4 equals x plus y. We'll look at a few other rules like this. Now, we can write this in terms of a Venn diagram. It's often helpful to write this in terms of a Venn diagram. So if every possible model, if we draw a picture showing every possible model, and then we draw a ring around all the models in which the knowledge base is true, and we draw a ring around all the models in which alpha is true, then saying that the knowledge base entails alpha is the same as saying that one of those sets is a subset of the other. So if the set of models in which the knowledge base is true, if that's a subset of the models in which alpha is true, then this entailment is correct. So let's look at a concrete example of this, again with the one-plus world. So we detect a breeze in square 2, 1. How many models are there which are consistent with the knowledge base that we've built up? Now, the other issue is relevant knowledge. So really, at this stage, we only have knowledge about these squares and not the other squares. So we can sort of restrict our consideration to just these 3 squares and not the others. And this goes back to the question about relevant, a task was considered fully observable if the percept contained all relevant knowledge about the world. So this is an issue about sort of relevant knowledge, but later on when we talk about probability, we'll talk about conditional probability, and this is the fringe, and so on. We'll go into this in a bit more detail, but for this point of, in this situation, when we talk about models, we're only going to consider truth assignments to these 3 squares. So, and whether they have a pit or not. So we know there isn't any one-plus there because of what we observed. It's just a question about the pits. So if we hadn't observed anything, we'd say, well, there's 3 squares there, and each one could either have a pit or not have a pit, so that gives 8 possible combinations, which are depicted here. So they could all have a pit, none of them could have a pit, 2 of them could have a pit, or 1 of them could have a pit. There's 8 possibilities. And then we can use this to draw a Venn diagram. So these 3 states here are the ones that are consistent with what we've observed, because we observed a breeze in 2-1 but not in 1-1. So after the observations, these are the models that are consistent with the observations. And then if we consider the proposition that it's safe to move into square 1, 2, this yellow boundary shows the square, the models in which it's safe to move into square 1, 2. And so because this knowledge base is a subset of that alpha 1, then we say that the knowledge base entails alpha 1. Okay? Now, to give a contrary example, let's suppose we're asking whether it's safe to move into square 2, 2. Well, that's represented by the purple. So you can see the red set is not a subset of the purple set, so it's not true to say that the knowledge base entails this proposition. Okay, any questions about this? All right, so now we get more to the formalism of logic. So we start with talking about propositional logic. So propositional logic just means that we have atomic sentences, we don't have variables, and we don't have quantifiers. So we have certain symbols that represent sentences, so we often use, it's often a capital letter with a subscript. So these are kind of atomic sentences, and then we have ways of putting sentences together. So if S is a sentence, we can write not S, and that's also a sentence. Now, again, there's different notation for and, or, and not. These are the ones that we're going to use for this course. So the not is this funny kind of hockey stick symbol, and an or. Sometimes it's easy to get confused between this, but the easiest way to remember it is that this symbol here looks like an A without the crossbar. So because this looks like an A, this is AND. If you know Latin, Latin is an interesting language. It has different words for inclusive and exclusive or, but the word for inclusive or is vel. So this V, looks like V for vel, but it's easier to remember this is A for AND. So this is AND, that's OR. And then we have these implication signs. S1 implies S2, and S1 if and only S2, right? So we have these ways of putting sentences together, and if we do it multiple times, we often put brackets to indicate the order in which these things are happening. So in the situation that we were just describing, or actually a related situation, the situation we were just describing, we were looking at whether there's a pit in 1, 2, 2, 2, or 3, 1. So these are our three proposition symbols in that ONPAS example. Now it's important, these are just subscripts, they're not yet variables. Later on we'll talk about how to make these things variables, but at the moment these are just three independent propositions. So each of these can be assigned either true or false, and we can build up a truth table showing 8 rows and every possible combination of true and false, and then look at what else would be true and false in each row. Okay. Now the way we do a truth table, this may seem obvious, but we've just got to sort of formalize it. So not S is true if and only if S is false. S1 and S2 is true if and only if S1 is true and S2 is true, and so on. Now S1 implies S2 is true if S1 is false or S2 is true. I'll say a little bit about that in a minute. And S1 if and only if S2 means either they have to both be true or both be false. Right, so if we want to know whether if we have a model in which this is true, this is false, and that's true, and we want to know whether this combined thing is true or not, we just apply these rules progressively. So false or true becomes true, and true and true becomes true. So we can build up a truth table. Now there's exercises, tutorial exercises to get you some practice at this. But here's a simple example. So let's say we have two propositions P and Q. We've got 4 possibilities about them being true or false. So you can figure out, these are 4 different models, so you can figure out not P is true in this case and false here. What about P and Q? P and Q is only true if both P and Q are true. It's false everywhere else. P or Q is false if P and Q are both false but true everywhere else. And the interesting one is this P implies Q. So P implies Q means that if P is true, then Q is true. So the only weird one here, the slightly unusual one perhaps, is this one here. What if they're both false? Okay, so the last line is where P and Q are both true. This is where P is Q but true, Q isn't. That's definitely false. If P is false and Q is true, that's true. But this top one is sort of interesting. What if both things are false? What does this really mean? Now, sometimes people say these things sarcastically. They say, if Fred has a job, then I'm the Pope, for example. What does that mean? Well, that means I'm so confident of the fact that Fred doesn't have a job that I'm going to make this statement that if Fred has a job, it implies something that I know to be false, right? But the proper way to look at this, the reason we get confused about this is we think about this as a causal we naturally tend to think of this as a causal relationship, that P being true somehow causes Q to be true. But that's really not the proper way to think about it. The proper way to think about it is that this is a rule, and we have to check whether we're sort of a policeman, and we have to check whether the rule is satisfied or not. And it often helps to actually think of a concrete situation. In all of this logical stuff, it often helps to think of a concrete example to help us to think clearly about this. So let's suppose you're working in a bar and your job is to serve people drinks, and you're told that by law you're not allowed to serve an alcoholic drink to someone who's under 18. So let's say that P is the proposition that Fred is served alcohol, and Q is the proposition that Fred is over 18 years old. Then P implies Q is the sentence, if Fred is served alcohol, then he must be over 18, right? So you think about this, you go to the bar, you go to a table to take the drinks order. Well, if Fred orders a club soda, if Fred orders a beer, then you have to check his ID to see whether he's over 18. If he orders a club soda, you don't have to bother checking whether he's over 18 or not, right? So this situation here is a situation where Fred is under 18 and ordering a Coke, whatever, not something without alcohol, so that's perfectly acceptable, right? So it's not that being over, it's not a causal relationship. It's not saying that you serve someone, and it's not like you serve someone alcohol and by magic they're over 18. That's not what's happening. What's happening is this can be either true or false, and you just have to check whether the rule is violated. So the situation, the only place where it's violated is if Fred is served alcohol but he's not over 18. Now, what about the rules? Well, okay, so if there's a breeze in square 1, 1, then there must either be a pit in 1, 2 or a pit in 2, 1. So we write that logically like this. And at the moment, because we only have propositional logic, we have to write a separate rule for every square. So if we're looking at square B21, there's a breeze in B21 only if there's a pit in 1, 1 or 2, 2 or 3, 1. It's got 3 neighbouring squares, and the ones in the middle have 4 neighbouring squares. And so you could write down 16 different rules, one relating to each square. Now, there's a bunch of inference rules that you can use to derive. So, as I mentioned, the game we're playing here is that you're given a bunch of sentences and a bunch of rules, and then you have to try to derive other sentences logically from the original ones. So, one way of doing this is kind of like a game where you just try to use these logical rules to derive new facts. And this is I've tried to, if you look, different sources give different lists of rules, but I've tried to compile a pretty authoritative one here. So, what do these actually mean? Okay, commutativity, P and Q is the same as Q and P. Associativity, P and Q and R is the same as P and Q and R. The same for OR. Distributivity of AND over OR. So P and Q or P and Q or R is the same as P and Q or P and R. And same with swapping the and or. And again, if you're not familiar with these, some of you may have seen this in the discrete math course or some other course. If you're not familiar with it, it's best to try to think of a concrete example. I'm not sure what's a good example. Fred has blonde hair and he's at the beach or he's in the cafe. That's the same as saying Fred has blonde hair and is at the beach, or Fred has blonde hair and is in the cafe. You know, you could think about it this way. Implication. So we were just looking at this truth table. You'll notice that P implies Q is the same as saying not P or Q. This is the same as saying that either Fred is not served alcohol or he is over 18. Oops. And then you have a few other rules. Idempotent. P and P is the same as P. Not P is the same as P. Contradiction. P and not P is always false. Excluded middle. P or not P is always true. And then the last one, you have De Morgan's laws. Not P and Q is the same as not P or not Q. So again, you try to think of an example. It's not true that I like broccoli and I like corn. That's the same as saying either I don't like broccoli or I don't like corn. All right. So, if a sentence is true in all models, then we say that it's a valid sentence. If it's false in all models, we say that it's unsatisfiable. And if it's true in some models and false in others, we say that it's satisfiable. So satisfiable means it's true sometimes. So these are the examples of things that are valid. A or not A. A implies A and A implies B implies B. These things are always true. And sometimes we use a kind of proof method called proof by contradiction or reductio ad absurdum. If the knowledge base entails A, that's the same as saying that if we add not A to the knowledge base, then it becomes unsatisfiable. So if we take the knowledge base and then assume not A, we derive a contradiction. There are no models in which this is true, but this is not true. So if you're kind of clever and get some practice at this, so you know, there's this game you can play where you're given one sentence and you have to try to prove a different sentence. Or prove that they're equivalent. And again, there's some tutorial questions where you can have a go at this. And yeah, if you're kind of a smart cookie and have some practice, you can use those deduction rules one by one to try to prove one thing from another. So in this particular case, B implies C is the same as not B or C. Right? So you can replace that. And then we can do distributivity of and over or. So this is the same as A and not B, or A and C. And then we can use we've got a not in here, so we can use De Morgan's laws to change this to this. And then we've got not something or something. We've got not A or B here. We can change that into A implies B. So this process kind of works, but it's like can be like searching for a needle in a haystack. There aren't any guaranteed rules there's no process. Well, this is, so far, we haven't got a process. What we would prefer is a bit more of a methodical way of doing this rather than kind of stumbling around trying to figure out which rule to use next. Okay, now there's this soundness and completeness. Now, so here we've seen this entail symbol. It looks like a two-legged table on its side. There's this other symbol that looks like a one-legged table on its side. And we say, so this symbol here means that in any model in which the knowledge base is true, alpha is also true. This here says that there's some way to derive, in this formal language, if you're given the knowledge base, there's a formal way to derive alpha. In other words, there's a process like this where you can go through rules one by one and prove that alpha is true formally. It may not be easy to find it, but it exists. And so you get this, these notions of soundness and completeness. So soundness says that if you can formally prove alpha from the knowledge base, then it must be true that the knowledge base entails alpha. Completeness says that if a certain logical formalism is complete, if whenever the knowledge base entails alpha, it's also true that you can formally prove alpha from the knowledge base. Now, it may seem trivial that we're even bringing this up, but I should mention the reason this makes sense. So with propositional logic is sound and complete. So in propositional logic, if the knowledge base entails alpha, then necessarily there's some way of proving alpha from the knowledge base. When we move on to first-order logic, it turns out that first-order logic is not complete. And in the early 20th century, even some of the most brilliant mathematicians of the early 20th century, like David Hilbert, were fooled into thinking that first-order logic should be complete. But Kurt Gödel, in 1933, Kurt Gödel proved that propositional logic is actually incomplete, which was quite a surprise at the time to many people, although today, of course, it's so well known that it's a bit hard for us to put ourselves back into the mind of the pre-Gödel people. But so that's why we raise this, is because this draws a distinction between predicate logic and first-order logic. One of them is complete, the other isn't. All right, where are we? So in predicate logic, this always exists, but we want to look at some methodical ways of finding it. Now, so there's a whole there's a whole course called Knowledge, Representation and Reasoning that's running, I think, next term or the term after. If you're interested in this logic stuff, you can take that course. You'll learn about this sort of thing in a lot more detail. We're just going to today in this course, we're only going to look briefly at some of the main points. So one way of doing this is that we convert it. So you're given a knowledge base and you're trying to look for a formal way of proving something. One way of doing this is to first convert the knowledge base into conjunctive normal form and then use a series of resolutions. So what do we mean by conjunctive normal form? Conjunctive normal form means that we write something as a conjunction of clauses, and each clause is a disjunction of literals, some of which may be negated. So this is an example of something that's in conjunctive normal form. Here's another example here. So conjunctive normal form means it's written as something and something and something and something and something and something. So it's a conjunction of things that are in brackets, and then each thing in the brackets has only or, not and, but some of these things can be negated, right? So it might be better to ask why these other things are not in conjunction. This is not conjunctive normal form because there's nested brackets. We're not allowed to have nested brackets. This is not conjunctive form because something in brackets is negated, and so on. So this is conjunctive normal form, and if you can look on the Wikipedia page about conjunctive normal form if you have any confusion about it. Okay, so this is the first step, is to convert the knowledge base into conjunctive normal form. And here's an example of how we can convert to conjunctive normal form. There's another example in the tutorial exercises. So how do we do this? Well, first we get rid of the double-ended arrow. So if we're just given any logical expression whatsoever, there's a process we can go through to convert it into conjunctive normal form. So the first step is to get rid of the double-ended arrow. If we see a double-ended arrow, we replace it with two single-ended arrows. So in this case, we replace, right, so this is telling us that if there's a breeze in 1-1, there's a pit in 1-2 or a pit in 2-1. So we first split this up and say, okay, this implies this and this implies this. So then we get rid of all the double-ended arrows. Then we get rid of the single-ended arrows by replacing alpha implies beta with not alpha or beta. So we replace this with this, and we replace this with this. Then the next step is to use De Morgan's laws to get rid of these negations of things that are in brackets. So not P1 or not P12 or P21 is the same as saying not P12 and not P21. And then finally we use distributivity of or over and to flatten out these nested brackets. So we change this into not P12 or B11 and not P21 or B11. So there's a mechanical procedure we can go through to turn any logical expression into this form. Now, how does this help us? Well, once it's in this form, then we can apply what's called resolution. And remember, this is a knowledge base. Because this is a conjunction, we can think of these things as separate facts within the knowledge base. So we know that this is true, and we know that this is true, and we know that this is true. So we can think of this as a list of facts. And so resolution is a way of taking two of these facts and deriving a new fact. And the way it works is as follows. We look for two facts, and we look for there has to be some proposition which occurs in both facts but is negated in one of them and not the other. Right, so here, in this case, if we look at this P22, here P12 occurs here and it occurs here and here, but it's negated here and not negated here. So we would be able to combine these two things by resolution and what happens is the two things that are negated cancel each other out. It's kind of like matter and antimatter. So we would cross these two out, and what we'd be left with is not B11 or P21 or B11. So this is sort of the general format. This is one of these clauses, and this is the other, and it has to be such that let's suppose that Li and Mj are negations of each other, then they cancel each other out, and then we collect together everything else. So here's another example. Let's suppose we happen to know this and this, then we can deduce this. Okay, and the reason is, well, in this case, we know that there must be either a pit in 1,3 or a pit in 2,2, but we also know that there isn't a pit in 2,2. If you combine these together, we can deduce, well, because there isn't a pit in 2,2, there must be one in 1,3, right? So it's pretty obvious in this case, and in fact, it's true in every case. Well, another way to say it is this is equivalent to saying that not Li implies everything else, and this is equivalent to saying that not Mj implies everything else. And we know it must be true that Li or Mj must be true because that's an excluded middle, and so we can deduce this. Okay? So this is always a logical consequence. So this gives us a kind of... The benefit of this is that before we had a list of 12 different rules and we weren't quite sure which one to apply at any given state. Here we've only got one rule, which is resolution. So it kind of makes the process a little bit simpler. We still have to look and try to decide what to resolve with what, but the other thing about this is we always gain knowledge. If we resolve two clauses, we get a new clause, but all the other clauses are still true. So if we make a mistake, it doesn't really matter. It just costs us a bit of time. Eventually we'll get where we want to go. So here's another sort of example, a bit more of a concrete example. So use resolution to prove that if there's a breeze in 1,1, there must also be a breeze in 2,2. So let's just go back to the picture to remind ourselves of what this is. So that's saying if there's a breeze here, there must also be a breeze here. Yeah? It's not something you might not have thought about something like that being true, but it's actually true because you think about it logically. If there's a breeze here, it must mean that there's a pit here or a pit here, and if there's a pit here or a pit here, there must be a breeze there, right? So we're just trying to formalize that. Okay, so first we take these sort of rules and flatten this into conjunctive normal form. So this, these three clauses here, right? So we started with this sentence here. There's a breeze in 1,1 if and only if there's a pit in 1,2 or a pit in 2,1. We converted that to conjunctive normal form. So these first three clauses come from there, but then we additionally add the fact that if there's a pit in 1,2, there's a breeze in 2,2, and if there's a pit in 2,1, there's a breeze in 2,2. So that's our knowledge base. And the thing we want to prove is that if there's a breeze in 1,1, then there's also a breeze in 2,2, right? So this is the thing we're trying to prove. So you just have to play this game and try to pick what to resolve with what. So here I've taken this clause and this clause, right? So the P12 appears here and not P12 occurs here. So they cancel and you collect everything else. And then once I've got this, I can resolve it with something else. So I can resolve this with this. The P21 cancels with the not P21 and I collect up this. So this is but this is where we sometimes have to use some of those very simple rules. So B22 or B22, that's the same as B22. So this here is equivalent to not B11 or B22, which is what we were attempting to prove. Now, there's a little bit of there's still a bit of complication here because we kind of have a target thing that we're trying to prove, but we can even get rid of that if we use reductio ad absurdum or proof by contradiction. So the even more automated way is to say, okay, this is what I'm trying to prove, so I'm going to assume the negation of that. So I'm going to negate this and add that to the database, and then what I do is I try to derive a contradiction. In other words, I try to derive an empty clause, right? If there's a line and if I end up with, let's say, P21 and I have not P21, then they would cancel each other out and I would just get nothing. And that's a proof by contradiction, okay? So have a look. Again, there's an exercise. One of the exercises from the textbook, it's about the unicorn being horned or magic. So please have a go at that exercise during the week and you probably will understand this somewhat better, and then you can discuss it in the following week's tutorial. So this is an example of a not fully automated, but relatively automated theorem proving mechanism. Is that I'm given a knowledge base and I convert it into conjunctive normal form using those rules. I have some alpha that I want to prove, so I assume the negation of alpha and add that to the knowledge base. If necessary, convert that to conjunctive normal form. So then I got a thing in conjunctive normal form that I want to prove is not satisfiable. So I do a series of resolutions until eventually I derive the empty clause. Or I might reach a situation where I can't do any more possible resolutions. Okay, so actually, I mean, when I said automated, this actually could be fully automated, but the only problem with it is that it may take an exponentially long time to run. If I've got a lot of variables, so I could write a program I could certainly write a program which automatically converts something into conjunctive normal form, and then I could write a program which repeatedly looks for opportunities for resolution and applies them, and I could just keep repeatedly doing that until one of these things happens. The problem is, this is kind of like the equivalent of random search. This is the equivalent of doing depth-first search or breadth-first search. I might just generate an exponentially large number of facts, but not get any closer to the thing that I'm trying to resolve. So it's instructive to think of this as analogous to uninformed search. And then the question becomes, well, is there some equivalent to informed search, right? So if you remember, we had the uninformed search methods where you had no idea whether you were getting closer to the goal or not, you were just searching randomly. And then we had the informed search methods where you try to direct the search to try to get closer to the goal. We would like to have something analogous to that in this situation. And there are ways of doing this. Now, again, like I mentioned, I'm just going to give a very brief summary of this. So the two main ways of doing this are called forward chaining and backward chaining. Now, before we do either of these, we have to convert the database into an even more restricted form, which is called horn clauses. So if you so we talked about, so in conjunctive normal form, in each of these brackets, you can have an arbitrary number of these can be negated. But in the Horn clause, it has to be in a form where if all of these things are true, then it implies something else. So it has to be in the form of a kind of implication. C1 and CD implies B. So what this means is that I think this is equivalent to saying that it's conjunctive normal form, but in each clause everything is negated except one. So if you had not A or not B or C, that would be the same as saying A and B implies C, right? So it's a more restricted form. In each clause, only one thing is allowed to be positive. So it's always of this form, something and something and something implies something else. And then we can do what's called, so this is a kind of resolution, but it's more restricted. It's saying, well, if we know P1 and we know P2 and we know up to Pn, and then we also happen to know that P1 and P2 and Pn implies Q, from these two things we can deduce Q. So if we can get the database into that form, then we can apply forward and backward chaining. So what are these things? Well, so forward chaining, we look for opportunities to apply this kind of rule. So we look for situations where we know this, and we also happen to know all of these things. So we look for places where we know P1 and we know P2 and we also know Pn, and we know that P1 and blah, blah, blah and Pn implies Q. Then we can apply that rule and add Q to the knowledge base. And we just keep repeating this until we run out of rules to apply, and hopefully, well, either we run out of rules to apply or we achieve the goal. So this is still, in a way, this is still a bit of sort of blind search, but it's searching, we've formalized the database in a bit more of a restrictive way, so that helps us to some extent. Now, but then what's the equivalent of informed search? Well, this is called backward chaining. So here we take account of the thing that we're trying to prove, right? We know that we're trying to prove alpha. So we look for a rule where alpha is on the right-hand side, let's say. And so then that guides the search, because it says, okay, well, if I can prove these things, then I can prove alpha. So then how can I prove those, right? So you choose so you effectively, they become sub-goals. So you start out, you maintain a list of sub-goals. So initially you've just got one goal, which is alpha. But then if you find a rule that says P and Q implies alpha, then you add P and Q to the list of sub-goals. And then if you find another rule that says that A and B implies P, you might add A and B to the list of sub-goals, because if you can prove A and B, then you can prove P, and if you manage to somehow prove Q as well, and you've got P and Q, then you can prove alpha. So this is kind of working backwards from the goal to try to guide the search by identifying the things that will help you to prove the goal. Okay, so forward chaining is data, as I said, this is just a brief summary, but generally speaking, forward chaining is data-driven, automatic, and unconscious, so it's like equivalent to breadth-first search in another context. So it might do lots of work that's actually irrelevant to the goal. It may prove lots and lots of things that have nothing to do with the goal. Now, backward chaining is goal-driven and seems more like problem solving. So if you think about how you deal with everyday situations in your life, my goal is to find my keys, right? So then you try to think about where could your keys be? Well, I might have put them I might have left them in the car. I might have left them on the kitchen table or by the front door. And then you kind of work backwards to you try to gain information that is very targeted, relevant to finding where your keys are. Or, yeah, how do I get into a PhD? I want to get into a PhD program, so I've got to have a bachelor's degree. I've got to enroll in certain courses. I've got to study hard and get good marks and so on. Or, I want to fly to New York, so I have to book a ticket, and then I have to get to the airport. And how am I going to get to the airport, and so on, right? So this is kind of a bit analogous to that. Now, just a few more slides before we take a break. I mentioned, we talked last week about constraint satisfaction. So satisfiability can be seen as a special kind of constraint satisfaction problem. So if we write down a logical expression, then when you're asking whether that is satisfiable, what you're actually asking is does there exist some assignment of truth values to those variables which makes this sentence true, right? So that's a constraint satisfaction problem. And often we try to write the database in what's called 3CNF. So 3CNF is a special case of conjunctive normal form where you put the additional restriction that each clause has to have no more than three symbols in it. So here's an example. This is written in 3CNF, and I could ask, is it possible to assign either true or false? Right, so the variables are these letters A, B, C, D, and E. The domains is true and false. I have to assign either true or false to each of those variables. And then how do we see this as constraints? Well, all of these things have to be true, so that imposes a constraint. If one of these clauses is false, then you're violating a constraint. So this is a kind of nice way of codifying constraint satisfaction problems, because if we convert something to 3CNF, we can actually sort of measure in a formal way, in a controlled way, how many constraints there are. And often, there's often methods of if you take something like the n-queens problem, often we convert it into 3CNF in order to kind of quantify these things. So there are methods by which you can take a constraint satisfaction problem and reformulate it somehow as a logical satisfiability problem. And so I mentioned before about, I haven't reproduced the graphic, but I showed this graphic where if the number of constraints is very small, the problem is easy, and if the number of constraints is large, the problem is easy. But for certain values, it can become very hard. And this gives us a way of kind of quantifying that. Because here, the number of variables is the number of letters, and the number of constraints is the number of clauses in this expression. And there's been a lot of kind of both empirical and formal work done on this, and somehow it turns out that there's this sort of critical value of 4.3, right? So n is the number of symbols and m is the number of clauses. So if you've got, say, 50 symbols, then you multiply 50 by 4.3, that gives you 230. Somehow that's like a magic number. If there's 50 symbols here and the number of clauses is much less than 230, then it's relatively easy to find a solution. If the number of clauses is much bigger than 230, then it's relatively easy to either find a solution or prove that none exists. But there's somehow this magic number of, if the number of clauses is exactly equal to 230, sorry, I'm not saying, not 230, is it? It's 215. If the number is exactly equal to 215, somehow these problems become very, very difficult. Yeah. Because they've kind of got just the right number of constraints to make the thing really hard. Okay, so just to summarize propositional logic, so syntax governs the formal structure of sentences, semantics governs the truth value of models, entailment is whether one thing necessarily makes another thing true, inference is whether you can derive something in a formal logic, and there's soundness and completeness, and propositional logic is both sound and complete. Now, just before we have a break, I'll just explain to you what's the limitation of first order of this predicate logic, and then after the break we'll move on to first order logic. So, as I mentioned, these subscripts are not variables, they're just independent sentences. So, in order to write down the rules of the Wumpus world, we have to write 16 different sentences, one about a breeze in square 1, 1, and 2, 1, and so on. And if the world got larger, we'd have to write down even more sentences, so the whole thing becomes unworkable. What we really want to do is to be able to make these things into variables, and instead of saying P12, we want to have something saying pit with two variables. So we want to say that this sentence says that there's a pit in I minus 1 and j, and this says that there's a breeze in square ij. So if we introduce these kind of variables, then we'd be able to get rid of these 16 rules and replace them with just one rule, which says that if there's a breeze in square ij if and only if there's a pit in I minus 1j, or there's a pit in I plus 1j, or there's a pit in ij minus 1, or there's a pit in ij plus 1, right? So by introducing these variables, it makes the logic much more powerful. Good. Okay, so let's take a 5-minute break, and then we'll come back and talk about first order logic.
Can I call it as implies? KB entails alpha. Can I call it as KB implies alpha with causality?
I'm not an expert in logic, but I think that we prefer to say this as entail rather than imply, because imply
Because
imply is a bit ambiguous.
so if I say call
Impl-
this as
yeah.
KB implies alpha along with causality, and I'm not really sure why you would say, if I say A implies B, you said it is not causal. All the time I was thinking it is causal.
I don't know. I don't know. Are you familiar with you're not? Are you familiar with Gödel's theorem or? So Gödel's theorem basically says that no matter how you formalize mathematics, there are going to be some statements which are true but cannot be proven. There are some statements which are true but they're not provable. So that's why people make this distinction. If something, these statements that are true but not provable, then the knowledge base entails them, but you can't formally prove that statement from the knowledge base. So the word imply is ambiguous. Imply usually means that you can formally prove it. Yeah.
Entails means you may or may not be able to prove it.
That's right. It is true, but you may or may not be able to prove that it's true.
Just can you tell what you are trying to tell me? I didn't understand what is this whole code thing supposed to mean?
These things represent the states in which it's safe to move into square 2, because there's no pit there.
This is KP and this is alpha. As in
Yeah, this alpha is where there's no pit in square 1, 2, and this is where there's no pit in square 2, 2.
So KB is the whole thing.
The KB is the red thing. So the KB entails that there's no pit in 1, 2, but it doesn't entail that there's no pit in 2, 2.
When you consider 2 to, why are we considering all these things? I didn't know. Because here we consider only one cell, but here, why is it 4 cells, 3 cells which we are considering? We are essentially considering 3.
The more important thing is these ones. These states here are consistent with the knowledge base, but it's not safe to move into. So the question we're trying to ask is, given what I know, is it safe to move to square 2, 2? And the answer is no, because there are these 2 states here where there's a pit in 2, 2.
Okay, so
Yeah, in a way, these states are not relevant because they're not consistent with the database. The important thing is this here. There are these 2 states that are in the knowledge base but not in alpha, whereas here, everything in the knowledge base was also in alpha.
okay, so we need not actually consider all these 3. We only need to consider these 3 and one more state.
These are models, but they're models that are not consistent with what we've observed. Yeah. So we can still reason about them, but we kind of already know that they're not true. But later on, I'll talk about situational calculus. Like this is true in the current situation, but something else, if we move to a different situation, it may include, later on we might be in one of these. So, yeah. Okay. Yeah.
I didn't understand what is E and which are the differences of this to this between this.
This means that if the knowledge base is true, then alpha is true. But this means that you can prove that you can formally prove that alpha is true using a proof method. So I could be resolution or
Okay, so
forward
this means
chaining.
that it exists a method to prove that
That's
alpha
right.
is true.
That's right.
And here we say that the difficulty is to find this ratio, but which ratio is good? Because here is under constraint. This is critical difficulty, this is over constraint, and which is the
Either these 2 are both good.
Under constrained.
Under constrained and over constrained is both good,
okay.
because under constrained you can easily find a solution. Over constrained you can easily either find one or prove that it doesn't exist. Yeah.
Another question: where we can find the marks of the first assignment?
Look, I'll put an announcement up how to
okay.
do it. Yeah.
Thank you.
I have a question about the activities in
Yeah.
classes. Why fn equals to minus jn is DFS?
Yeah, it's the reason is because what this means is that the longer gn, you'll explore the nodes with the longer gn first.
Yes.
So let's say you've just expanded this node. If you just expanded this node, that means it must have the longest path. And then because you've expanded it, its children must have an even longer path. And so this already had a longer path than anything else. The children are even longer. So that means that you must explore these children before you explore anything else. And that's the determining property of DFS. But among DFS, this actually, it does a really bad job. This algorithm it is a kind of DFS, but it does a really bad job because it actually explores the worst possible path first. Yeah. But it is a kind of DFS. Yeah. It's just something that I don't know if there's any formal proof about this, but it's just people have run lots and lots of experiments generating random clauses, and somehow they've found that this 4.3, I don't know where this really came from, but there's a whole kind of area of mathematics involved with this.
Like for the meaning of m,
Yeah.
then, like m is number of clauses means the number of directions.
The number of these things is m. So here it's 1, 2, 3, 4, 5.
And then it's the number of distinct symbols.
That's right. Yeah, so A, B, C, D, E. So here m is 5 and n is also 5. Yeah, to make it hard, you would have to have 4 times as many clauses. Yeah. With respect to. Good. Okay, so now we move on to first order logic. So in first order logic we have objects which could be people, houses, numbers, years, colors, or anything. We don't impose any types normally. This just could be anything. Then we have predicates which say properties of things. So red, whether something is red or round or prime, whether one thing is bigger than another, whether one thing is inside another, so on. So these relate either properties of one object or things that relate two or more objects to each other. And then we also have functions. So the father of X or the successor of X or something. So we've got objects, predicates, and functions. Now, again, speaking about logics in general, if you take that knowledge, representation, and reasoning course, they go into much more detail about this. We're only going to talk about prepositional and first-order logic, but there are other logicians study other kinds of logic. So there's temporal logic, probability theory, fuzzy logic, mode, and also modal logic and other things. But we're just going to look at these two. So So again, looking at the one-piece world as an example, the kind of constants we would look at would be squares like 1, 2 or 3, 1. We look at things like the objects like the gold or the one-piece or the arrow. And then predicates might be telling us that two squares are adjacent to each other, or that there's a smell in a particular square or a breeze, or that the agent is at a particular place. Functions, so the result, when we get to situational calculus, we'll explain the importance of this result function. And then we can have variables. We normally use letters for variables like x, y, a, t, and sorry, I think the mic was possibly muted. Sorry about that, if it didn't go on the recording. So I was just explaining what kind of things we have in the one-piece world. So from predicate logic, we still have these connectives and or not and arrows. But in addition, we have some extra things that are only for predicate logic that we didn't see in propositional logic. So we have equality, whether one object is equal to another. And we also have these quantifiers for all and there exists. So the upside down A is for all and this is there exists. So how can we use these things to put together sentences? Well, an atomic sentence is usually a predicate and then several terms in brackets. And a term can either be an atom or it can be a function of other terms, or it can be a constant or a variable. So an example of a sentence would be at agent 11S0. So this is saying that in state or situation S0, the agent is at 1, 1. And this is saying that in situation S5, the agent is holding the gold. So we will see that when we do planning, we'll see that it's actually useful to put this to say whether things are true in a certain situation rather than whether they're just true or false generally. So these are atomic sentences, and then we can put them together using the connectives from predicate logic. So we can get sentences like this. There's a pit at X, and X is adjacent to Y. Right, so then we get to these quantifiers. So the upside down A says that something is true for all values of a certain variable. So this sentence here says that where there's glitter, there's gold. So for all X, glitter X implies at gold X, right? So we get this kind of uppercase semantics where we put the verb first. Instead of saying the gold is at X, we say at gold X. So it's kind of like verb, subject, object, or whatever. But you get used to it after a while. And so this is equivalent to a conjunction of instantiations of X. So when we say for all X, glitter X implies at gold X, that's equivalent to saying, well, if there's a glitter at 1, 1, then there's gold at 1, 1, and if there's a glitter at 1, 2, there's gold at 1, 2, and so on. So we sum all of this up with one statement, and that's basically the power of this first-order logic, is this being able to collect all of these together in one statement. Now, there's just a few kind of rules of thumb that you get used to see if sometimes something looks suspicious in logic. So typically, the arrow, when you see the for all, it usually goes with the implication sign. So it's quite common to see things that say for all something, something implies something. These are two things that just very often go together, the for all and the implies. It's very rare to see for all combined with and it's logically, there's nothing really wrong with it. So if I say for all x glitter x and at gold x, that's a well-formed sentence, but it's generally not very useful because it's making too strong a statement. This is saying that for all x, there's glitter everywhere and there's gold everywhere. So it's saying something very strong, and it's rare that a statement with this kind of generality would be true. And then the other quantifier is the existential quantifier, the back to front E. So there exists x such that sheep x and black x. So that means there exists a black sheep, or some sheep are black, and this is equivalent to having a whole series of disjunction of a whole set of sentences. So this is saying that, you know, maybe Dolly is a sheep and Dolly is black, or Lassie is a sheep and Lassie is black. One of those statements has to be true. Not all of them, but at least one of them. And again, we sort of have this rule of thumb that there exists often goes with and. Because if you had there exists combined with an implication, this would be too weak a statement. There exists x such that sheep x implies black x. That's a very, very weak statement. Because in order for this to be true, it just means there has to exist some object that isn't a sheep. And then this would be true. And now, logicians love to come up with these kind of slightly absurd sounding sentences, and there's a lot of jokes about, very nerdy jokes about logicians. So I think one of the jokes goes like this, that there's a philosopher, a mathematician and a physicist. There's a philosopher, a mathematician and a physicist, and they're all on a train going from England into Scotland. And the train crosses the border, and they look out the window and they see a black sheep, and the physicist immediately says, "Oh, that's quite interesting. In Scotland, all the sheep are black." And the mathematician says, "Well, no, we can't really conclude that. All we can conclude is that in Scotland, some of the sheep are black." And the philosopher says, "Well, really, all we can say for sure is that there's at least one sheep in Scotland, and one side of it is black." And there's also, logicians talk about the existence of black swans too. Like when British people came and colonised Australia, before they assumed before that all swans are white, but when they got to Western Australia, they saw that the swans there are black. So this is sort of an example about how you can't necessarily generalise from what you've previously observed. Okay, then we can combine these operators. So we combine the quantifiers now, and sometimes we can swap the order and sometimes not. So you've got to sort of think carefully about some of these things. So if I say for all x for all y, that's the same as saying for all y for all x. And so I can swap those, and if it's there exists, I can also swap it. But if I've got a for all and a there exists, I'm not allowed to swap them. You know, there exists x such that for all y is not the same as for all y there exists x. Now, why is that? Well, so this is the classic example. There's this famous sentence for every man loves a woman. Now, when I was an undergraduate at Sydney University, I took a computational linguistics course from a guy called Christian Matheson, and he said when he first learned about logic in Sweden, people kept coming up with this example of every man loves a woman, and he always thought this was kind of a weird sentence that no one would see in real life. But after he graduated, he got a job as a postdoc at UCLA, and he flew to Los Angeles, and when he was in the taxi on the way from the airport to the university, he saw a big billboard that was an advertisement for perfume, and it literally said, every man loves a woman. So he realized that this is not a made-up sentence, this is actually a real-world sentence. So if I say that every man loves a woman, there's two ways of interpreting this. It could be that for each man there's some woman that he loves, but for different men it's different women, right? Or you could interpret it to say, well, there's one particular woman, maybe some famous movie star, and every man in the world loves that particular woman, right? So this is illustrated here. If I say there exists an X such that for all Y loves XY, that means there's one person, and that person loves everybody. But if I say for all Y there exists X that loves XY, that means for every person in the world there's some person that loves that person, but it's different people for different people, right? So you can sort of have a think about the difference between these two things. But this is something that often as I said, these different motifs. So often you often see for all in combination with implies, you often see there exists in combination with and you do often see this as well. I didn't write this down, but if you wrote this symbol twice, there's a saying that for every upside down A there exists a back to front E. Now, there's an equivalent of De Morgan. If you go back to, I think it was De Morgan's laws governing negation. Sorry, let's just go back to this. Let's think about this De Morgan law, not P and Q, if and only if not P or not Q. There's kind of an equivalent version of this which swaps the universal and existential quantifiers. God, sorry, I've collected all of today's into one file. So if I say for all X likes X ice cream, that's the same as not exists X not like. So again, if you think of a concrete example, this kind of makes sense. If I think about if I claim that everybody likes ice cream, if that's false, then for that to be false, it means that there exists one person who doesn't like ice cream. And if I say that there's a person who likes broccoli, then you know it's not true that everybody doesn't like broccoli. Yeah. So this is kind of the quantificational version of De Morgan's laws. Now, the good thing about this is you guys have been through all those prologue exercises, and so you're kind of familiar with this in a way because you'll see that this is very closely related to the prologue exercises, in particular the family exercises. So we can try to take an ordinary sentence and translate it into logic. So what does it mean if we say that brothers are siblings? Well, for all X and Y, if X is the brother of Y, then X is also a sibling of Y. Sibling is symmetric. For all X, Y, if X is a sibling of Y, then Y is a sibling of X. So sibling is just a generic, we didn't have this in our example, but sibling is a generic word for either a brother or a sister. This thing we did see with the prologue, right? So a mother is a female parent, so for all X, Y, if X is the mother of Y, that means X is female, and X is the parent of Y, and those two things are equivalent. and the first cousin, if x and y are first cousins, that means there exists P and PS such that P is the parent of x and P is the sibling of Q and Q is the parent of Y, right? So I think we formulated this in a slightly different way in terms of we didn't have siblings, so we actually had to say that there was someone who was the parent of both P and PS, and P was not equal to PS. Okay, so you're kind of familiar with this. All right, so how would all this relate to the Wumpus world? Well, these are the sort of rules that we would have for the Wumpus world. So for all x and... Now notice we've brought time into the equation here. So if the agent is at x at time t and detects a smell, then that must mean that that location is smelly. And if there's a pit at x and x is adjacent to y, then there'll be a breeze in y. And this is a double-headed implication. So it's also true that if there's a breeze in y, then there must exist a pit x, so there must exist an x such that x is a pit and x is adjacent to y. And so we can put these two together as a as an equivalence. So for all y, if y is breezy if and only if there exists x such that x is a pit and x is adjacent to y. So this is how we can write rules for the Wumpus world. Now, you'll notice in the beginning maybe we think of this as being time, but time is only useful if you know exactly the actions you're going to take. We want to be able to search in such a way that we consider different possible actions. So if it's now time step 2, if I take this action, then I'll be in one square in time step 3, and if I take a different action, I'll be in another square. So instead of time, it's actually better to think of this as situations. So in a particular situation, something would be true. So rather than saying holding gold, we want to say, oh, I'm holding gold now, or in some other situation, and then if I do a particular action, then I'm going to move from one situation to another, or we could one state to another. This is the equivalent of a state in state-based search, but it's sometimes convenient to think of it as we sometimes use the term situation rather than state. So this is where this result function comes in. If I'm in state S and I do action A, then I'll get into a new state which is called result AS, right? So here, if I move forward, I was in square 1, 1, but when I moved forward, I'm now in square 1, 2. So with this framework, we have enough formalism now to actually build a plan for the Wumpus world or a similar task, right? We want a plan is, remember, a plan is a series of actions. So this is similar to what we were doing in weeks 3 and 4, but instead of the successor state in the Rubik's Cube and so on, we had a certain state, and if you did a certain action, you could explicitly say what the next state was going to be. But here, a state is really defined by what's true or false in that state. So we can say that if in a certain situation I'm at the gold and then I do a grab action, then in the resulting state I will be holding the gold. So these states are kind of defined not explicitly but implicitly by these rules that tell you what's going to be true in the next state. Now, when you try to apply these in the real world, you get what's known as the frame problem. So, you know, this rule says, well, this sounds a bit funny to talk about this, but, you know, I'm holding the arrow. So remember, you're given an arrow at the beginning, and you can shoot the arrow. So one of the things you've got to keep track of in the game is whether or not you still have the arrow. And if I have the arrow and then I pick up the gold, I'm going to still have the arrow. Now, it sounds obvious to say that, but there are a lot of these kind of situations with this formal logic, things that are true, and this is sort of what we call common sense reasoning. You know, we sort of know by common sense that picking up the gold is not going to make any difference to whether I have the arrow or not. But if you started to put in explicit rules to say all of these common sense things, then the number of rules just kind of blows up exponentially. So we often just make the assumption that if something was true before, it remains true unless something happens that makes it false. Right? But in the sort of expert systems of the 1980s, there was this idea in the 80s of expert systems where you could just codify everything into rules and plan everything out, but these systems ran into difficulty because of this common sense reasoning. And, you know, here's some examples. You know, if a cup is red and you turn it upside down, it's still going to be red. But if the cup is full of water and I turn it upside down, it'll no longer be full of water. We know that because we can sort of do a physical simulation in our head and imagine what's going to happen. But if you have a system that's purely logical and doesn't have that kind of physical embodiment or intuition, then you'd have to put that in as an explicit rule. Yeah. And again, you know, people have written about this, you know, related issues, the qualification problem and the ramification problem. So normally we expect actions to have a certain effect, but in the real world, you could have endless caveats. You know, normally, if the gold is there and I try to grab it, I expect that I'll be holding it afterwards. But then you can say, well, what happens if the gold is slippery? What happens if the gold is nailed to the floor? What happens if it's too heavy for me to pick up? And also the ramification problem. So, yeah, in general, we assume that a fact is true if a rule tells us that an action made it true, or if it was true before and no action made it false. So we need these kind of simplifying assumptions in order to solve these problems. But in the real world, there are certain things that happen very slowly. So every day, my shoes get worn down a little bit, and my clothes get worn out a little bit. And I don't normally think about that from one day to the next, but eventually it's going to reach a point where my shirt is so worn that I have to throw it away and get a new shirt, and the same with my shoes. And it's not easy to encode that kind of consideration into these logical models. Okay. So getting back to the one-plus world, how do we make a plan? Well, in very simple situations, we can just kind of try to find a plan as a series of nested actions. So this is a very simple situation where the agent is at 1, 1 and the gold is at 1, 2. all we would have to do is move forward and grab, and then we would be holding the gold. But if we want to make a longer plan, this is how we have to kind of approach this. That what we're looking for is a sequence of actions such that if we were to start in the initial state and perform those actions one after another, we would eventually, a certain thing will be true, like that we're holding the gold. And so this is kind of the result of the plan, is that series of actions. And so what we're asking is, the plan result is if we start in state S and execute all of those actions one after another, where would we end up? And so the search problem can be codified as saying, does there exist a plan such that after executing that plan, we would be in a certain situation, and in that situation we would be holding the gold. Okay, so if the gold happens to be at 2-1, then the plan would simply be forward and grab. But in general, if I'm in a state S and I execute no actions, then I'm going to again be in S. Again, since you're familiar with Prolog, it's easier to understand this, that we always think of a base case and a recursion. So the base case is that if we execute the empty plan, we're just in the same state. Now, if the plan isn't empty, it must have a head and a tail. So the result of this combined plan would be that, assuming that we do the first action first, this would be the same as if we did action A on state S, and then we applied the tail onto that result. Yeah. So this is the same as when we were trying to concatenate two lists or whatever. And there are planning systems which are kind of special purpose reasoners designed to find these plans more efficiently than a general purpose reasoner, right? So as I said, like this, again, this idea of informed versus uninformed search. So the naive way to solve this would be just to try every possible action in like a breadth first search until somehow you find the right plan. But if you can implement forward chaining or backward chaining, especially backward chaining, then you can probably find a plan faster. Okay, so the summary. First order logic contains objects and relations, form of semantic primitives, then we put them together using the same as predicate logic, but in addition, equality and quantifiers. So this gives us increased expressive power that's sufficient to find things like the Wumpus world, and we can use the situation calculus to describe actions and change and formulate inference on a knowledge base. Any questions about this? Good. Well, since we're a bit ahead of time, I'm going to actually start on the next topic. Just a little bit. So the next topic is going to be machine learning. Oops. Learning and decision trees. Yeah, so I'll just briefly introduce this. Okay, so again we go back to our description of agents. So we had reactive agents, we had model-based agents, we had planning agents, we had adversarial agents, which we talked about in week 5 with the games, and then the last type of agent we just mentioned was learning agents. And I mentioned that we treat learning not as a separate module, but as a way of improving existing modules. So probably next week we'll talk about reinforcement learning, how you can learn to make better actions. There are ways to improve. There are ways to learn to improve planning and your world model, but what I want to focus on just now and next week is perception, how to improve perception through what's called statistical learning. So there's actually 3 types of learning. Machine learning is divided into supervised learning, reinforcement learning, and unsupervised learning. So with supervised learning in this course we're only going to talk about supervised and reinforcement learning, not unsupervised, but it's an important, unsupervised learning is also important. And what's the difference between these 3 things? Well, with supervised learning you're given examples of inputs and outputs. So I'm trying to think in terms of an agent. Yeah, I said that statistical learning was a way of improving perception. So if you're learning to play RoboCup, for example, the inputs might be images from the camera, and you might be wanting to learn whether the ball is in the image or not, or where the ball is in the image. So in the simplest case, perhaps the input, you collect a series of images, and some of them have the ball and some of them don't, and then you try to learn from a given image whether it contains the ball. You know, that's just one kind of simple example. Here's another example from the textbook. This is a bit of a contrived example, but you're going to a restaurant and you're trying to, let's say you've got a bunch of restaurants to choose from, you want to go out to dinner, and you're trying to predict whether someone will wait for a table at that restaurant. You know, they get to the restaurant and all the tables are full. Will they say, okay, I'm going to stay and wait in the restaurant, or will they say, oh, no, that's okay, I'll just go away and go to another restaurant? So it's a bit of a contrived example, but it gives you, it helps you to see some of the elements of this. So you have a bunch of other attributes that describe the restaurant, and then you've got this one attribute that you're trying to predict. So the one we're trying to predict is the one on the right-hand side there, whether the person will wait or not, so it's either true or false. And these other things are attributes of the restaurant. So the first one is whether there's an alternative restaurant available. You know, is there another restaurant across the street, or is this the only restaurant in that neighborhood? So that's true or false. And then, does the restaurant have a bar? It's going to be more pleasant to sit and wait if there's a bar there. FS is whether it's a Friday or Saturday night, or is it a weekday. How hungry you are. Are you very hungry, or are you only mildly hungry? How many patrons are there in the restaurant? Is it full? Is it empty, or is it sort of partially full? What's the price? Is it an expensive restaurant or a cheap one, or medium? Is it raining? does the restaurant take reservations or not, and what kind of food is there, and what's the estimated waiting time. The person tells you that they expect that there'll be a table available in 20 minutes or 40 minutes or 60 minutes. So you're given all of these inputs, and then you have to predict that output. And this framework is called supervised learning. So we're given these examples, and so these, you're given a list of examples of situations that have previously arisen, and then you're supposed to learn from this to try to predict what will happen in a new situation. So a new situation arises where there's other values of these input variables, and from that you have to try to predict whether the person will wait or not. So that's called supervised learning. Now, there's another kind of learning called so the supervised learning, you're given the input and you're told what the answer should be. Right? Reinforcement learning, you're not actually told what the answer should be. So reinforcement learning is more a situation where you're moving around, you're acting in an environment, and at every time step you're in a state and you have to choose a certain action, and then you move into another state, and then you get rewards. So you choose one action and you get a reward of $5 or whatever, but you choose another action and you get a punishment, someone takes away $2. Right? So just based on, you're never actually told what action you should have taken. The reward signals tell you give you some idea of whether what you did was a good action or a bad action. That's called reinforcement learning. And then with unsupervised learning, the agent is only presented with the inputs. They're just presented with some data, and the aim is to actually just try to extract some structure out of that data. Okay, so as I mentioned with supervised learning, we have a training set, and usually we have a test set. So what I showed you with I showed you some examples with the restaurant. That's called the training data, and then we always assume that other situations are going to arise, so they would form what's called the test set. So there's some set of other examples that we haven't seen, and after we've finished learning, we want to try to see whether we get those examples correct or not. So there's always this distinction between the training set and the test set, and the aim is to predict the target value based on the input attributes. Now, there's various kinds of learning paradigms available. Some of you may have, some of you may have previously enrolled in the machine learning course or might do it in another term. Machine learning course, of course, focuses on this stuff and goes through a lot of different learning algorithms. For this course, we're just going to look at decision trees and neural networks, but there's also k-means, k-nearest neighbor, support vector machine, and various other paradigms. Now, in practice with supervised learning, so we have to choose the learning method, but often we have to choose a representation of the inputs and outputs. We might have to do some pre-processing of the input before we feed it to the learner. When we get the output, sometimes we need to do post-processing. But another important factor is generalization. We want to avoid overfitting. Okay, so this is an example of a machine learning problem. So we got the independent variable is x, and the dependent variable is f of x. So this is the kind of thing you may have seen in high school physics class, where you build you tie a heavy object to a string and you measure the length of the string and you swing it back and forth as a pendulum and you measure how long it takes to swing back and forth. You know, that's one example. Or you have a hockey table and you have a puck, you hit a puck with a certain speed and then you measure the distance it travels, or you build a little electrical circuit and you measure the length of the wire compared to the resistance or whatever. You know, there's many situations where you have one variable that you can adjust and you have something else that you're trying to predict, and you only can do a certain number of measurements, but then what you want to do is try to draw a curve here to predict what would happen. Well, what would happen if I picked a different value of x? What value of f of x could I expect? Okay. Now, sometimes we just try to fit a straight line to those data. This is probably the best line that we can draw. Sometimes we might have like a parabola instead of a straight line, or we might have a fourth order polynomial, or we could just draw something really crazy, but still going through the points. So I'm interested in your opinion. Which of these four models do you think would do the best job of predicting the unseen points? So who thinks the straight line is a good choice? Who thinks the parabola is a good choice? Yeah, a few of you. Who thinks the quartic? Who thinks this is good? We can see this looks ridiculous, but it's an interesting philosophical question. Why shouldn't you pick the yellow crazy curve? It does, after all, go through all the points, right? So why is the yellow curve bad compared to, say, the green or the blue curve? Yes?
Because discontinuities in slope in places where we happen to be.
It's got discontinuities, yes, that's right. And you don't expect, right, so you have an expectation. If this data is really coming from some underlying, like, physical process or whatever, you expect it to be smooth. That's what you're saying, right? You expect the physical process probably wouldn't have that many discontinuities. All the zigzags. It looks very unnatural.
In places that you don't have a data point to suggest that there might be a change in applications, and sort of like how far the gap between, say, the last two points, you have that big E in there.
That's right. Yeah. So it's sort of, but notice that we're making an assumption here. We're assuming not only that the curve should fit the points, but we have a preference among curves that fit the points. A smooth curve is better than a jagged one, right? A smooth curve is more likely to to be true, yeah? More or less. Does everyone agree? Does anyone else want to say something, phrase it differently, or? Very sensitive to change, yeah, that's right. Which seems unnatural, yeah. So this, there's a general principle here. I mean, another way probably of saying the same thing is that these ones are in some sense, these are simpler models. You know, the straight line is kind of simple in the sense that it's defined by only two parameters. The quadratic is defined by three parameters, and this is defined by four or five parameters. So these models are sort of simpler, but still match the data. This one is complicated. You know, because it's got all these twists and turns, you would need a lot of parameters to define this. You know, so this is sort of one way of looking at it. And this principle is often referred to as Occam's razor. It's named after someone who lived in the 14th century in Britain called William of Ockham. He wasn't the first person to say this, but he really kind of popularized it. And basically what he said was that if you've got a number of different hypotheses and all of them are consistent with the data, you're best to choose the simplest model. You should choose the most likely hypothesis is the simplest one that's consistent with the data. Now that's his original formulation, and the phrase Occam's razor, in the beginning, Occam's razor just referred to William of Ockham as a person. He was called a razor because he had a razor-sharp mind. But in the 19th century, people kind of had this idea of Occam's razor as if it's like some sort of knife that cuts away unnecessary complexity, which is kind of a very nice image. Now, in the modern interpretation of this, our modern interpretation is a little bit more general than what William of Ockham really said. We think of it as a trade-off between the complexity of the model and how well it fits the data. So here's another example. Let's suppose we have two input, in this case it's a classification task. We have two input variables, and the task is to draw a curve which separates the circles from the crosses. Because when I give you a new point, you're going to have to tell me whether you expect it to be a circle or a cross, right? So this model here is very simple. It's just a straight line. This model here is sort of very complicated. This one here, we kind of feel like this draws a good compromise, that it's a bit more complicated. It's not as simple as this, but it's not as complicated as that. And it does a pretty good job of fitting the data, but it gets a couple of them wrong. And we kind of assume that maybe these points are mistakes somehow. They were like mislabeled or something. Yeah. So often we're just looking for this compromise between simplicity and accuracy. And it's an interesting question, like how can we accept this if it really misclassifies these data? How can we accept this as an answer? Well, the only answer is that you have to assume that there may be mistakes in the data. So there's two possible kinds of mistakes in the data. Sometimes the data just get mislabeled, like that cross was meant to be a circle, but by human error, someone accidentally made it a cross. Or maybe these values were measured wrongly, like someone tried to measure this value and that value, but they got it a little bit wrong, so actually maybe the cross was supposed to be here, but was actually here. So it's interesting, some of you picked the green line and some the blue line, and in fact, we can't really definitively say which of them is better, because the answer really depends on how much confidence you have that the data is accurate. So if we choose the green line, what we're basically saying is we're excluding that point. We're saying this point must be some kind of mistake that, again, as I say, like maybe someone measured it wrong, either measured X wrongly or measured Y wrongly. Maybe X should have been over here, or maybe Y should have been up here. Somehow like there was a mistake in the measurement. Or if it's just a little bit off the line, it could be errors in the mechanism that does the measurement. You know, it can only measure it to 1 decimal place instead of 2 decimal places. So If we have a suspicion there may be mistakes in the data, then we would probably prefer the green curve. If we're very, very sure that the data is really correct, then we might prefer the blue curve, because we're sure that that point is not a mistake, so we prefer a model that's a bit more complicated but fits all the data, right? So the choice between these things sometimes depends on your assumptions about how accurate the data is. Any questions about that? Now, this is another, so a point like this would be called an outlier. Now, this is another famous case of an outlier. This is from the 2000 presidential election in the United States. This is this is probably the closest one of the closest elections in history. George Bush won the election by one state, and the state of Florida was won by less than 1,000 votes. I think according to the last count, it was about 150 votes. And some people went in and analysed what was going on in that state, and this graph shows for each county in Florida how many votes were predicted from election polling and how many votes the candidates actually received. And it turned out that there was another candidate at that election called Pat Buchanan, who was running for the Reform Party, and he was a very minor candidate, but somehow in one particular county he got a lot more votes than was expected. So you can see for all the other counties the polling gives a good prediction of the actual votes, but this is an outlier. From the polling, it was only predicted that this guy would get about 500 votes, but in fact he got about 5,000. This is a logarithmic scale, so he actually got 10 times more votes than was predicted. And this seems very suspicious because Palm Beach has a lot of Jewish voters, and Pat Buchanan had made some favourable comments about Adolf Hitler, calling him a strong leader and so on. So it's a bit hard to believe that these people really wanted to vote for Pat Buchanan. So this happens in the scientific method as well. When you see an outlier like that, you sort of try to look for some other explanation. And the explanation is that, in the United States, it's not like Australia where the ballots are all centrally designed by the Electoral Commission. Somehow each county designs its own ballot papers, and the ballot paper in Palm Beach had this funny kind of butterfly pattern. So the Republican and Democrat is here, and Pat Buchanan is over here. So the assumption, the most logical assumption is that these people, they saw that these people probably wanted to vote Democrat, and so they punched out the second hole, but somehow by mistake they ended up voting for Pat Buchanan. Yeah. So often it's, from seeing an outlier, you go back and look for some other cause. Okay, just a couple more slides, and then we'll take a bit of an early break. So we go back to this restaurant training data. So I'll just, so next week we're going to talk about neural networks, and decision trees. We're going to talk about decision trees and then neural networks, but I'll just introduce decision trees now and then we'll talk in more detail. So one way to try to learn these data is with what's called a decision tree, and most of you, again, are probably familiar with this. Some of you may have seen this in another course, but you've probably seen something like this in high school where you're trying to classify different plants and animals. You have you have little rules that say is the animal warm-blooded or cold-blooded? And then if it's warm-blooded, then you ask whether it has feathers or not. And if it has feathers, then it's a bird. And then you ask whether it has fur or not. And so by asking a series of questions, you can kind of narrow it down and eventually say what the animal is. Right? So you've probably seen that before. Now, in this situation, you just pick one of these attributes. So we've got 11 attributes to choose from. Let's say we pick an attribute which is patrons. So that divides the data set into 3 pieces. Patrons can be none, some, or full. So there's only one case where there's no patrons. There's 1, 2, 3, 4 cases where there's some patrons and the rest it's full. Now, so that divides this into 3 pieces. Now, if you look at the attribute we're trying to predict, the one case where there was no patrons, the person didn't wait. So this is, the kind of herd mentality. People think, well, if there's no one in that restaurant, then it must be a really bad restaurant, so I'm not going to eat there either. And if there's some patrons, then the answer is true. Basically, because if the thing's not completely full, that means you have a better chance of getting a table. Either you can get a table straight away, or maybe there isn't a table that's large enough for your group, but the fact that there's some tables available gives you confidence that you'll be able to sit down quite soon. So if there's no patrons, this is false. If there's some, this is true. So we don't have to further subdivide these cases, but then if it's full, then you get to the question of you have to look at some other attribute. So the cases where it's full, sometimes it's true and sometimes false. So then we choose a new attribute. So we might choose the weight estimate. So if it turns out that if the weight estimate is less than 10 minutes, people will always wait. If it's bigger than an hour, they never will wait. Now, these intermediate values, if it's 10 to 30 or 30 to 60, then you've got to subdivide further. So there are many different ways to build a decision tree. We just have to choose the order in which to split these attributes. So we chose to split on patrons here, and then split on weight estimate, and then on hungry. But if we had chosen a different attribute in the beginning, we'd get a different tree, right? And here's an example of another possible tree. In some sense, this is the best possible tree because it's short, it's smaller. It might be better just to first test on patrons. As I mentioned, if there's none or some, then we have a classification. Now, if it's full, sorry, where's the other tree? So we already split on patrons, but then we looked at weight estimate. Instead of weight estimate, it might be better to ask whether you're very hungry. So if the thing is full and you're not very hungry, then you're not going to wait. And if you are hungry, instead of looking at the weight estimate, maybe the type of food is more informative. If it's a French restaurant, I'm always going to wait. If it's Italian, I'm never going to wait. If it's burger, I'll wait. If it's Thai food, it depends whether it's a Friday or Saturday. I mean, this reflects the behavior of a particular individual, I suppose. But, okay, what's the point of this? Well, you see, I've got 2 different trees here, but one of them is bigger than the other. Now, both of these trees classify the training data correctly, if I trace through all of these examples that I'm given, this tree correctly says whether it's classified as true or false, and the other tree also does so. But because the other tree is smaller, we might prefer it, right? So we kind of think of this in terms of Occam's razor. The large tree we think of as being like this because it's complicated. The smaller tree we think of as being like this because it's kind of simpler in a way, right? We're trying to apply Occam's razor. We want to have we want a simpler model that's consistent with the data, and we assume that a smaller tree means that it's a simpler model. So ideally, we want to choose to split on these attributes in an order which will give us a small tree rather than a big one in order to be consistent with Occam's razor, because if the assumption is that there's some unseen, I can see this is my training data, but there's some other data that's coming later that'll be the test data, and I believe that if I have a smaller tree, it'll have a better chance of correctly classifying the test data. Okay, so this is what we're going to look at next week. The first thing we look at next week will be how can we build this tree? How can we have a process that chooses the attributes in such a way that we get a small tree instead of a big tree? Okay. Any questions about this? Okay. We've been through a lot of material today. I think we'll have a half-hour early break today, and then we'll pick this up next week. Because of the remaining values. So you want to try to keep as many remaining values as possible for the other regions. So this way, if only one value would be left for these two regions, but here there's two values left.
Yeah, I know, but this is a different color. But I think maybe this one and this one maybe also okay for this.
This is just about which color to choose.
Okay.
If you want to know, yeah, this is in a way it's a bad example because it would be better to, if you're choosing a region to color, it would be better to choose this or this.
I think maybe. So this only constrains the color.
That's right.
Okay. And also the forwarding checking use the same rule of this. Also use this circle because I don't know why.
That's right.
Okay.
Yeah, it's just a more sophisticated way of eliminating. It uses sophisticated reasoning to eliminate more possibilities. Yeah.
So when I know this, when I know this is when I arrive this, so I should go back and change the other color.
That's right.
So if red is stop and maybe I will choose the green or other.
Yeah.
Go on the same. same as step.
Sorry, say it again.
Sorry. If just if we should stop at this step.
Yeah.
And maybe I need to change the color, maybe green, and repeat this.
Yeah, you have to back because there was no choice left here, so then you have to kind of go back and try something else.
Okay, thank you.
Question
Yeah,
we need to assign the number of groups.
that's right.
There are a lot of
Yeah.
if one every percent is good, or we need to find a pattern.
No. Anything that gives this pruning pattern is good.
Because, for example, you're 10, 11, or 11, 10. It's
There are many
30%.
different. Yeah, exactly.
So everything is
Any of them is good.
Thank you.
In terms of this kind of problem,
Yeah.
I can understand this function, the time complexity. Because I tried, the B is branch vector, for example, is
This is if you go all the way to the end of the game, then the size of the tree will be.
take this for example,
Yeah.
the B is 2,
Yeah.
and the M is probably should be 3 or
2.
2.
Because we
Why is
treat
that?
this as depth 0, depth. Yeah.
So we count the
the
2
root-
phases
Yeah, exactly.
or 2 depths.
That's right.
So the time complexity should be 4.
That's right.
So what is 4 means? It's
Well,
like
in the worst case, you may have to explore all of these.
explore 4 nodes.
That's right.
I mean, this called nodes and this didn't call nodes. Doesn't call nodes or because when we apply the alpha beta
yeah.
algorithm, we have to like this. I think all of them this should be nodes instead of this.
So it's let me just try to find the. I can just show you here. This goes back to the depth first search or whatever. That it's that search. Yeah, so this level is b to the d, or b to the m, that's b to the m minus 1.
okay.
So you get this sum, but in fact, this is kind of proportional to b to the d.
Proportional. So the O means it's not exactly the 4.
Yeah, it's not
4
exact.
units
That's
of time.
That's right.
So it's a kind of
It's
relationship.
times are constants. Yeah.
Okay,
Yeah.
got it. So the question is that in the assignment 2,
Yeah.
the last question is explain why. I mean, we have to calculate the time complexity of the alpha beta search and explain why why we get this. So
It doesn't have to be a formal
yeah.
proof. Really, what I'm just looking for is, if you read this, so like at every second step,
Yep.
you expand all the nodes, and then in the other steps you only expand one.
Yeah.
So instead of getting b times b times b times b, you get like b times 1 times b times 1 times b times 1. So that's
So-
why you get b to the d
I'm
over 2 or whatever
Yeah,
it
I'm
is.
over
Yeah,
2.
m over
So
2.
all I have to explain is only why we get a smaller value
That's right.
inside the O function.
Exactly.
So, okay, got that. And another question is that, in terms of this one,
Yeah.
the final question is that we have to get a best heuristic.
Yeah.
But here we already have been given one, and my heuristic function is that just like find the vertical
Yeah.
distance and plus the horizontal distance to find the heuristic value. I mean, in
It's, sorry, can we go back? Yeah. The thing is, because you're allowed to move diagonally,
yeah, I'm not allowed to
you,
move diagonally.
if you can move diagonally, then
Yeah.
you can move, you can go faster.
Yeah.
So this is,
Yeah. So this is the diagonally heuristic. So I think this one is diagonally.
no, because you're allowed to move diagonally.
I mean, below, before the question B,
Yeah.
I already got two heuristic. So in the third question of, do I need to find out a new heuristic? Because before the question B, I already got two. One is
This one's not admissible anymore because, like, let's say this is 3 and this is 5.
Yep.
Right, so 3 plus 5 is 8.
Yep.
But actually, I can do this in 5 moves. I just go 1, 2, 3, 4, 5. So this is not admissible because it's bigger than the real answer.
Oh, I understand that.
Yeah.
And beside the assignment, I got a question about machine learning.
Yeah.
As you mentioned, there are some paradigms
Yeah.
of machine learning, neural networks, and for machine learning.
Yeah.
And I'm currently working on a project, a kind of problem about plotting a kind of like three-dimensional,
Yeah.
like I need to plot a three-dimensional form, like something like that.
Yeah.
So I need to do hundreds of experiments to plot it. So my project is that how to use the machine learning to only just need to do 26 experiments data. So the machine learning could plot this kind of graph.
Maybe I'll just see if some other people have maybe shorter questions,
Okay,
and then we can come back to this. Yeah,
Okay.
yeah. No, it's okay. no.
As I understand,
Yeah.
the next question is about 3. So we have to ask is he empty, actually empty?
Yeah, I don't think there's. I don't think there's a better. Well, maybe empty is a tree. Yeah, I don't think there's a better solution because you would have to. This way you can get away with just 1 or 2 base cases, right? If you didn't want this as a base, well, there's 2 answers. So the first question is maybe empty is a tree, in which case you would need this. But if you don't think empty is a tree, the problem is you would need several base cases. You would need a base case where both are empty. You'd need a base case where this is empty but not this, and you'd need a case where this is empty and not this. So it's simpler to just say that empty is a tree. Yeah.
No, I don't know how to solve question 4.
Yeah.
And so this is not the last problem. Do you the idea?
Yeah, so it's good to think of some examples, and I mean, if you look at
This is my son.
right.
I don't know how to.
Right. Well, the first thing is
This is our question 5.
can I edit this or? I mean, I think what you need is it really depends not on whether that number is positive, but the relationship between the first 2 numbers. So you need to say sine runs, like you have to consider, let's say there's x and then y,
Yes.
and then where's the pipe?
Which one?
Where's the vertical thing here?
Yes.
Rest. Something, right. So then we fill this in a minute, but then it's, okay, so what does this mean? So let's say x and y have the same sign.
Yes, and it's some sign.
So if x and y, so let's say x is, well, you might have a predicate that says what's the same sign, but let's say x is greater than 0 and y is also greater than 0, then they'd have the same sign, right? I don't know what's going on here.
Yes, maybe it's okay. It's good.
Well, then what would happen, if they have the same sign, then that means that y is already part of a sublist.
Yes,
You just
y
have to
is-
add x to the front. So what's going to happen here is you're going to have so x will be added to an existing list. And then there'll be some other tail. Now, what would happen if... Okay, so then sign runs... Let's see. If you just had y and rest, then this should produce like one... I think it's like this. So you've got to consider the first two elements. Yeah, so if you just had y and rest without x, then y would get put into some run and then something else, and then you just have to take that and add x to the front of it.
Yes, add to the so add y to the front of it.
That's right.
So how to add it? Y is.
You see the logic, the flow goes like this. It'll come down here, compute this, and then add x to the front.
So add y. You mean add x to the front?
That's right. It'll add x to the front of this sublist.
Yes. So the rest is correct.
Well, you have to have rules that take account of the first two elements,
Yes.
not
yes.
just the first element. That's the issue. You have to. You need like x, y, and rest rather than just having item and rest, because it depends on the value of the first two elements.
Yes.
So you need this rule. Maybe you should have a separate predicate that says that x and y are the same sign, and then another rule for when they're different. So if they're different signs, then x becomes a new list by itself.
Yes.
Yeah.
Okay. Understand. Okay, I'll do it.
Hi. I don't know if you remember me. I came.
Oh, yes. Oh, sorry, I forgot about this. Did you send me email?
Yeah, I think she has sent you an email from DataSort.
Let me just check.
So we have an event coming up next week, actually.
Yes.
Yeah. So the undergrads, they're organizing this alumni sort of an alumni meet. Industrial professionals are coming.
Mm-hmm.
So yeah.
Let me just check. I get so many emails.
She told me that she sent it last
Very likely, but
Yeah.
Oh, you sent it? No.
No,
someone-
it was the president that day.
What was her name?
Sharon. No, it came from hello@datasoft.com. At datasoft.com. You haven't received anything?
It should have gone here. I'm just checking another email, but put it in the conversion. that's a couple of years ago.
I can ask her to send it again.
Yeah, maybe it went astray.
Maybe, yeah, okay. Spam or something like that, maybe.
All folders.
Oh, okay, it's all folders. So I'll ask her to send it again then. That's
Yeah,
fine.
maybe that's
Yeah.
good. It's either.
Yeah, so that's what we have an event coming up next week. Is there?
Okay.
Yeah. So.
Oh yeah, when is that?
I can get you more details with respect to that.
Yeah.
But so they're calling industrial professionals
Yeah.
next week. So they have already called one Chinese student,
Right.
old student. So we're just wondering if you know anyone else who we can call.
To speak.
Yeah. Who had done MIT.
I can. Sorry.
Oh no, that's okay.
Look, I'll try to find a graduate from MIT
Yeah.
who would come and talk about data science.
Yeah. Data science AI.
I can't think of anyone straight away, but I
Oh,
will
no,
try
that's
to
fine.
have
You
a
can
think.
take your time. Yeah, you can
Do
just.
do
let
you
us
know which day this event is?
I can get you more details with respect to that. Could you
Yeah.
just give me your actual email address? I don't know if she sent it to the wrong one, so I'll just note it down.
Look, it might be safer to send it to my Gmail.
Okay, so
It's Alan David Blair. Yeah. Just because I guess so many.
yeah. Awesome. Yep. Okay, I will ask her to send it again to this particular email address.
Okay. Oh yes. Oh yeah. Oh sorry. Yeah. Oh, you want to have a look? Yeah. Oh, you want to have a look at the panel and stuff? Yeah. So these are. So I
Which one
normally
do you
use the
normally
lapel. I normally use this, and I think it's this one here. So you got to make sure this is not muted. At the beginning, after the break, I still had this muted, so you've got to be a bit careful. And
So
then
this one is muted.
that's right. I don't know what. Oh, that must be from the computer, I think. And then you can adjust the volume here. And then the room control. So the lighting, I normally have the lectern off, just so
It should be off.
people can see the slides better. And then the room lights, this is the maximum lighting we can get here. It's fully on. And then, I don't know if you were here at the beginning, but I was having trouble with my laptop. Do you have videos and stuff? Or just, yeah. So.
I can just put it